Hi guys, you've got another batch of quizzes that are coming back to you, and I know some of you are kind of frustrated trying to figure out like how do you get better at those, and what does a satisfactory answer look like. So I figured I would go through the most recent round of quizzes, at least for the chemistry stuff that you've been doing, and give you my version of what I would see as, like everything that would be in a completely full answer. Now, you don't have to have every single aspect of this in order to get to satisfactory, because again, satisfactory just means you've done enough to show me that you can use the concept, that you can function with the concept, that you can apply the concept. And until you get there, you won't get that S that you're striving for. So the quiz that you guys had, the first quiz, quiz 1, was, okay, so you've got a carbon and you've got a hydrogen, and if they come up near each other, will they have some sort of interaction? All right, so the mental program I run in my head, which a lot of you guys are getting pretty solid at, is to figure out, okay, what's their current electron status when they kind of roll up near each other? Because that's going to determine what kind of interaction they have, if any. So when we look at the periodic table, we see that carbon is in group 4A, so that means that we can do our carbon, we draw it like that. It's got 4 valence electrons. And our hydrogen, I'll do it in a different color. Our hydrogen has 1 valence electron because it's in group 1A. All right, so looking at these, my brain runs through whether or not they're already stable. Because if they're already stable with their electron arrangement, then they're not going to bond with anything else. Because bonding is all about, will a bond make them more stable than they currently are? And if the bond would make them more stable, then that's a bond you should predict would happen. So when I look at these, it looks like carbon has room for 4 more electrons. Switch back to this. So you could do 1, 2, 3. There's 4 spots available around carbon for additional electrons. And then for hydrogen, it's got 1 spot available. Because remember, hydrogen is tiny. So it only has the first shell of electrons, which means it'll have a full shell if it's got 2 electrons, because that's the only shell it has is that first one, and that first one is full at 2. So hydrogen is going to be more stable if it can get access to 1 more electron. So anything that gives it access to 1 more electron is probably going to happen, because things that make things more stable tend to happen. Carbon, anytime it can get at least 1 more electron, it can get access to another electron, that's going to make carbon more stable. Now, a lot of you have pointed out that, maybe this one interaction between 1 carbon and 1 hydrogen isn't going to solve all of carbon's problems. It's not going to make carbon as stable as it could possibly be in the whole universe. But we're interested in, would this one interaction between just these 2 atoms make carbon at all more stable? Would it help it get towards stability? And if it would, then we would predict that would happen, knowing, as you guys have pointed out, that 1 bond isn't going to fix all of carbon's problems. So that's fine. All right, so we know that neither one of them is stable currently, which means that we should predict that they may interact, because the interaction may make them more stable. So when we look at carbon, there's a few ways to predict what's going to happen between them, right? So hydrogen would like another electron. Carbon needs some more electrons to be stable. So we've got the situation where we have to figure out, okay, so then when they go up against each other, what do we predict would happen? Now, for hydrogen, so if I take all these guys off, we just have that situation. If hydrogen could somehow pull in, say, this electron, kind of draw it over to itself, that would make hydrogen more stable, right? But carbon is kind of doing the same thing. So carbon is eyeing hydrogen, saying, okay, well, if I could get access to that electron, then I'd be more stable. So now we have to consider that atoms don't help each other out on purpose. They don't do what's nice. They do whatever they need to become more stable. They do whatever is possible for them. So we're going to have more information about, okay, so if they both would be more stable if they could pull an electron away from the other one, then what's the matchup actually going to look like? So you guys have gotten pretty used to looking at electronegativities for each of these things. If you have an electronegativity table in front of you, then great. You can look up and say, okay, electronegativity for carbon is 2.5 and for hydrogen is 2.1. If you don't have electronegativity tables in front of you, this can still be done, right? So you can use the periodic table to help you predict basically what the electronegativities will be between these things. So the farther over to the right and towards the top of the periodic table you are, the more electronegative you are. So the harder you pull on electrons. Now, hydrogen's a tricky one because hydrogen is way over on the left side of the periodic table, but its electronegativity is surprisingly high for what it is. So if you're going to use the periodic table as your indicator of what something's electronegativity is, hydrogen is that exception you're going to have to remember, all right? That hydrogen is located way over on the left side of the periodic table, but it's much more electronegative than anybody else that's that far over on the left. Some of you have learned the trick of metals and nonmetals from a chemistry class. So you can use a lot of different ways to know what this interaction is going to be like. Now, some of you pointed to this and said, okay, so the difference here, there's a difference in their strength. Carbon's more powerful in terms of electronegativity, so probably carbon will steal an electron away and they won't share. Now, if you're trying to figure this out and you're like, is it possible that carbon might steal because it's stronger? Well, you have to think about how much stronger does an atom have to be to actually rip an electron away from another atom. So if you look at the fact that this exists, right? So you know that this exists, and you may not know the exact electronegativities of oxygen and hydrogen off the top of your head. Over time, you may get better at that. But we know that this is a covalent bond. So oxygen and hydrogen have shared electrons. Same thing here, shared electrons. So we're looking at shared electrons there. So that means that oxygen is not strong enough to steal. All right, so because we're always trying to figure out, is this going to be a steal or is it going to be a share? Now, if oxygen is not strong enough to steal from hydrogen, and we think about where things are on the periodic table, and we look at carbon, carbon isn't even as strong as oxygen. Carbon is weaker than oxygen when it comes to electronegativity. So if oxygen can't steal electrons from hydrogen, carbon definitely can't. So I'm just giving you guys, when you get really good at these, when you've had enough practice, when you're really functioning with these ideas, this is what I mean. Even when you don't have every bit of information, you're so solid on the ideas that you're like, well, I can get at that a lot of different ways. All right, so that's kind of what we've established here. There's a lot of ways to know. You can look at the electronegativity table. You can look at where things are on the periodic table, or you can think about something that you know exists and compare it to that. The other thing we talked about a bit was we have certain cutoffs where if you're looking at the difference in electronegativity, so difference in electronegativity is like in this case saying, okay, 2.5 for carbon, 2.1 for hydrogen, so the difference between them is 0.4. Now we typically say that if you have an electronegativity difference of greater than or equal to 2, then that's going to be a steal is possible. Now this is nowhere near 2. So that means carbon is just nowhere near strong enough to steal from hydrogen. So this is going to have to be a share. And sharing is something you're forced to do when you're not strong enough to steal. That is incredibly important to understand. Stealing is kind of ideal for most atoms. It's better if you can just own that electron 100% yourself and not have to share it. You get forced to share because the atom you're going up against puts up enough of a fight for those electrons. So we've got the situation where we've got carbon and hydrogen are going to be sharing. So we're going to draw that in there. Right? We've determined that they can't steal. So we've got that guy, and then we've got hydrogens. So then we're going to draw that they have a bond because they were forced to share. So now we've got a bond between them. We can represent it this way as well. We've still got those other valence electrons hanging out. So as you guys pointed out, carbon is not 100% stable yet, but just this one bond has helped it become more stable. Hydrogen is now quite stable because hydrogen now has access to these 2 electrons, and that makes hydrogen have a full octet. So that's the first step, all right? We figured out what kind of bond. So first of all, yes, they will interact. They would be more stable if they bonded, so they bond. A steal is not possible because the electronegativities are too similar. So now we know they're going to have to share electrons. We're not done yet. If you're asked how 2 things are going to interact and potentially bond, it's one thing to say they're going to share. So that means you've got a covalent bond. But now you have to say what kind of covalent bond. So is it polar or nonpolar? So in this case, we got to go back to the electronegativity to look at that, right? So when we look at carbon and hydrogen, we've got carbon is at 2.5, hydrogen's at 2.1. The difference between them, so the electronegativity difference, is 0.4. Now, typically speaking, and you can remember these cutoffs, you can kind of just remember, there's a lot of ways to get at this. Again, there's more than one way to get at this information. But you'll find in a lot of textbooks that the cutoff that's given, let me clear a little space here. So we've got this kind of cutoff where if you've got an electronegativity difference of around 2 or more than 2, then a steal is possible. But if you have an electronegativity difference of less than 0.5, then you're going to see that listed in textbooks as a nonpolar bond. Now, if you have an electronegativity difference of greater than 0.5, that's going to be a polar bond. And those cutoffs can be useful. They can be little shortcuts for you to just, think about these things. You'll also get really used to looking at certain bonds and just knowing how they are. So carbon-hydrogen bonds, we're going to see so much in physiology that you're just going to get really used to this. So we know carbon-hydrogen, the difference between the two on electronegativity is 0.4. So that's going to be this one, right? So that's less than 0.5. So yes, there's an electronegativity difference between them, but it's just not that big a deal. They're really, really close in terms of their strength. So when they're sharing those electrons are pretty much equal back and forth. Maybe occasionally an extra loop around carbon, but pretty much back and forth equally. So that means there's nowhere where electrons are piling up. And once we know that, that means we're not going to assign any kind of charges here. This is not going to act magnetic. So this is going to be a nonpolar covalent bond. That was quiz 1. So that's all the levels of thinking you have to do. I'm not going to deny that that's a lot of thinking that you have to do. And eventually the goal is to get so good at thinking through those steps that no matter what pair of atoms I give you, you automatically run through that. Okay, what does that atom look like? Is it stable with its electrons currently? If not, it's going to bond. Will a steal be possible? If not a steal, then a share. If it's sharing, is it going to be equal sharing or not equal sharing? And how do I know that? So that's a lot of things to go through. So now you've determined that. So we'll clear that away. And then the next part of the problem was you were given this molecule. So CH4. Right, so if you already did the work of figuring out, and we'll label these in a different color, all of these bonds, and the nice thing about this molecule is it's the same bond over and over again. So these are nonpolar covalent bonds. There's no pileup of electrons in any particular place. The sharing is quite equal. So that means that this particular molecule has no possible way of behaving like a magnet. So what we have to think about here is multiple layers of thinking again. You had to ask yourself about what those bonds are like. And then once you figured out what the bonds are like, then you're looking at the entire molecule and saying, is this molecule, is this thing, this whole thing, is this thing polar? So is it a magnet? Because we have certain substances that act like magnets. Water acts like a magnet. Polar molecules act like magnets. So we're asking, does CH4 act like a magnet? And in order for something to act like a magnet, you have to be able to kind of draw it as a box and say, all right, one end of it has a positive charge and one end of it has a negative charge. And generally speaking, we mean like slightly positive and negative. So if you can look at this picture and say, oh yeah, I can find a place where I've got slightly negatives on one side and slightly positives on another side, then you're looking at something that's magnetic, something that's going to be polar, it's going to mix with water, all those things. When I look at this picture, everything in this picture is nonpolar. It's made completely out of nonpolar bonds. There's nowhere where electrons are piling up. That means there's no possibility for it to act like a magnet. So that means this thing is a nonpolar molecule. So 2 different times in your levels of thinking where you're going to be asked about polar versus nonpolar, okay? So you get asked about bonds, like this bond. Is this bond polar or nonpolar? So the electrons, are they spending equal amounts of time around each atom, or are they being pulled towards one atom more than the other? Then you have to kind of zoom out and look at your entire molecule. So once you've looked at your bonds, you're going to look at the molecule and say, okay, does this thing act polar or nonpolar? So if I give you a different example, so that example was nonpolar covalent bonds and then a nonpolar molecule. But let's look at, you guys had a quiz last week. Let's look at this one. You had this situation last week. Looks superficially similar, right? But when you run the electronegativity stuff and you do that whole mental program of like where do electrons spend their time, when you look at how electrons are between these two, you're going to find that they're doing more like this, right? So they're spending a lot more time around fluorine. So the way we're going to designate that is we're going to say, okay, that particular kind of bond, we do these little things where we're like, look for the electrons that way. So another way we can show that is, okay, here's our little slightly negative, and that leaves carbon slightly positive. So I'm just going to erase that vector right there. We can think about it that way. So in this case, what we're looking at here, so this is a polar bond, right? And so we can go through each of these sets of things and be like, okay, same thing here. A lot of loops around fluorine, occasional loops around carbon. So this is also a polar bond. So we can go, okay, slightly negative there, slightly positive around carbon. Same thing here. A lot of loops around fluorine, occasional loops around carbon. So this end's going to end up slightly negative. Same thing here. A lot of loops around fluorine. Fluorine's very electronegative. It's going to keep it most of the time. So it's going to give a little negative flavor to that end. All right. So when we look at this situation, we've got polar bond here, polar bond here, polar bond here, and polar bond here. The whole thing is made out of nothing but polar bonds, 100% polar bonds. But now we have to ask, okay, now if I look at this whole molecule, I have to try and figure out, is it going to act like a magnet? So is there a way that I can draw this thing so that I get something that looks like that? Where I can draw a line through it and have all the negatives be on one side of the line and all the positives be on the other side of the line. So you kind of run this mental check and be like, okay, what if I did like this? If I do that, do I have a left side, right side that's positive and negative? Well, no, I've got negative here, but then negative here and here. All right, well, then what if I cut it this way? Can I make it be a magnet that way? Nope, still got negative, 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 negative. What if I cut it right down the middle? Nope, still have the same problem. So this is the weird thing. This molecule is made 100% out of polar bonds, but the whole molecule is a non-polar, that's a terrible way of writing that, non-polar molecule. So you have to ask, when you're being asked about those words, polar and non-polar, and we're thinking magnetic and non-magnetic, a molecule can be made of polar bonds, but still be a non-polar molecule. So once you've built your whole thing, you've figured out what the bonds look like, you need to do that final step of looking at the molecule and saying, can I slice this thing any way to put the positives on one side and the negatives on the other side? If I can do that, then the molecule is polar. It's going to act like a magnet. It's going to be drawn to other magnetic things. If I can't draw a line like that, then I've got a non-polar molecule, and this thing is going to be non-magnetic. And it is not going to mix with magnetic things. It's going to act like a clay bead. It's just not going to be interested. So that's kind of how to think about quizzes 1 and 2. And then I'll address quiz 4, which was about diffusion, separately. So if you want to look at that one, you're going to check that separate video.